Good morning to everyone. I'm Davide Dermit, student of the 23rd cycle Electronic and Telecommunication course, and my tutor is Professor Mattia Borgarino. Today I will show my research activity about frequency synthesizer based on digital phase lock loop. So this is the structure of the presentation. I'll begin the talk starting from an analog, fractional, and frequency synthesizer, and then I will list the motivation that will lead several research groups in the past year to investigate about the possibility of digital intensive PLL. Then I will describe the standard design flow and proceed describing the design assistant that I propose in order to simplify this task. And concluding, I will show the block of the PLL that were realized at transistor level as a conclusion of the work. So here we have an analog fractional and frequency synthesizer based on PLL, which is a loop able to lock its output frequency to a highly stable low noise reference signal. And this architecture, the fractional and synthesizer, is used to break the trade-off between bandwidth and resolution that is typical in integer and synthesizer, because in both the loop, the PFD pulses and then the charge pump pulses are at frequency equal to FRF, and then to correctly average them, the loop must have a bandwidth much lower than the reference frequency. But in integer and synthesizer, the frequency resolution is exactly equal to the reference frequency. And this means that in order to achieve a high resolution, I need to use a low reference frequency. But this in turn implies a low bandwidth. And since the switching time is inversely proportional to the bandwidth, the trade-off arises because a low bandwidth may mean a too high switching time. Today the trend is to keep scaling technologies down, and this leads to an easier digital design, but the loop that I have just shown is analog in nature, and this unfortunately realizing analog block in deep submicron technology is not easy at all. For example, because the limited supply voltage poses a serious limit on the number of devices that can be stacked. And a more serious problem in this kind of application, the time domain resolution of digital signal is higher than the voltage resolution of analog signal. For this reason, starting from about 2001, a lot of research has been carried out in order to realize PLL based on digital techniques, and the ADPLL depicted in the high part of the slide were born. In the first day of ADPLL, however, the DCO digital controlled oscillator noise performance were much worse than the VCO LC tank VCO counterpart. And so there is the possibility to convert back to the analog domain the control voltage and then using a VCO in place of the DCO. This kind of architecture is known as the DPLL, depicted in the bottom part of the picture. So the standard design flow starts from the communication standard for which the synthesizer is meant, and from here the overall phase noise specification and the sparse content specification and switching time are derived. And then from this overall specification, they are broken down into pieces in order to define the parameter and the specification of all the single building blocks of the loop. And this, together with the domain linear time invariant model in the frequency domain as the one depicted here and the control system theory, are used together in order to design the loop starting from its open loop transfer function. This is, however, a tricky process because it's full of maths, and if something needs to be changed in the LTI model, this means to carry out the design process again. So, for this reason, I propose a design assistant developed in MATLAB that I have developed during my internship in Entropic Communications of Antipolis, France, during 2008. Here you can see the graphical user interface that allow to define all the parameters that I have listed in the previous slide, and allow the designer to build its own LTI model in terms of Simulink blocks. And then just by clicking on the highlighted button, the design assistant designed the loop in order to meet the specified requirement. and also plot the output phase noise, both the overall noise and the noise produced at the output from each of the contributor, as you can see in the bottom part of the slide. The power of this approach is that seeing how some modification of the LTI model impacts on the output phase noise and of the response of the PLL is just a matter of few clicks. Of course, this kind of model is not able to describe the transient response of the loop. And for this reason, we have compared the result obtained by this approach with an equivalent nonlinear Simulink model solved in the time domain, obtaining a good correspondence that proves that the software is working properly. Okay, for both, for time concern, we were not able to close the entire loop at transistor level. So in the frame of cooperation with the University of Nice, we have decided to integrate on silicon only one version of the TDC and one digital divider, but realized using two different flip-flops. The general architecture that we have adopted, however, is depicted in this slide, and with the n divided by 2 and 3 cell is able to produce all the division model between 2 to the power of n and 2 to the power of n plus 1 minus 1. The working principle of this architecture is not very intuitive because the signals are flowing in both directions. So to simplify, here I have depicted the inside of one cell and the output signal that are obtained from starting from a fixed input signal and varying all the possible combination of the control bits that are mod in and p. And as you can see in the left-hand corner of the slide, the output frequency is equal to 1/3 of the input 1, only if both P and mod in are high. Otherwise, the output frequency is 1/2 of the input 1. Okay. Here, there is the structure of the divider, so it is able to, it receives at the input frequencies between 1.2 gig and 3.5 gig, and provides all division model between 12 and 35. The first version of the digital divider that we have realized is based on the SCL source coupled logic flip-flop that is also depicted in this slide. Since the SCL logic has a voltage swing that is much different from the CMOS logic, that is the basis of the programmable digital counter at the end of the chain, we have inserted between the blocks two level adapters that adapt both the SCL signal to the CMOS signal from left to right and vice versa from right to left. As I have said, we have a lot of possible input frequencies and a lot of possible division models. So trying to reporting all the transient simulation response in one or more slide doesn't make sense. So here I have decided to depict just one of the simulation result transient response for a given input frequency that is highlighted in the left-hand part of the slide, and for a given division model. And in addition, I have added some phase noise simulation results. The SCL logic, that is the heart of the previous architecture, is known to be very fast, but is also known to consume a lot of power. So we have decided to do another version of the same prescaler, so same input frequency range, as you can see, and same division model, but this time realized based on a TSPC flip-flop that is shown in the bottom part of the slide. The TSPC logic is, as of course, a voltage swing that is well adapted to the CMOS logic. So here we do not need any level adapter between the cell, and as predicted, gives a much lower power consumption, being almost 1/4 of the previous slide in the worst case corner. Okay, again, here just one example of the simulated transient response, and again, some phase noise simulation results. And to conclude, here I have reported the chip, the layout of the 3 chips that we have realized at transistor level, and we have taped out at them at the end of November 2009. So now we are waiting for the chip to come back from the foundry in order to perform on-wafer measurement. Okay, this concludes my presentation. I would like to thank the Anthropic guys, the University of Nice, and in particular for FED, and of course all of you for your kind attention. If there are any questions, it will be a pleasure for me to answer you. Thank you again.